I welcome back all to the course on Control System Engineering. In this video, we are going to learn the time response analysis of first order and second order systems. Before going to the first order and second order time response analysis, let me recall what we have discussed in the previous video. We have discussed or we have learned already the mathematical modeling of mechanical, translational systems and rotational systems, and mathematical modeling of electrical systems. And after that, we have also learned how to convert or how to develop the equivalent electrical model from the given mechanical model using force voltage analysis and force current analysis. In addition, we also have learned the basic principle of DC servo motor and how to derive the transfer function of DC servo motor and AC servo motor transfer function derivation, and also we have learned the basic principle of synchros and how it will work as the error detector. In this video, we are going to learn the time response of first order systems and with the standard input signals like unit step and unit impulse, sine wave and parabolic signal and so on. And also in further videos we'll also learn the time response of second order systems with standard input signal and what are the time domain specifications in first order time response and in second order time response, and also finally we will learn the steady state error and time constant and error constants. So in this video we will concentrate on time response of first order system with standard input signal. Now let us see the time response of first order system only in this video. Yeah, before going to time response of first order systems, let me explain what is meant by time response. In general, what is the response? Response is nothing but an output of a system. The time response is nothing but response of the system in time domain. So, why to find the time response? After designing a system, we have to verify how the system is responding for various input conditions. So we need to verify the time response of a system for different input signals. That is the motive of the time response analysis of a system. In this example, we'll see the closed loop control system is shown here. The response of the system is C of t in time domain and the input is R of t in time domain. Then the system is having some transfer function. So the response can be found by using the transfer function and the input. You can also find the time response of a system using the differential equations by writing the differential equations and solving those. But the difficulty is when the system is a higher order system, then it's very difficult to solve directly in time domain that higher order differential equations. Due to that complexity, we will take the Laplace transforms help. So using this transfer function in Laplace domain and the input in Laplace domain, by solving these two, we can find the response of a system in first Laplace domain, then we can convert into time domain. In this example, the system transfer function is given as m of s. Since it is a single closed loop system, By the transfer function of closed loop system, we have that m of s is equal to g of s by 1 plus g of s into h of s. Forward gain by 1 plus forward gain into feedback gain. Here g of s is the forward gain and h of s is the feedback gain. Therefore, the overall loop gain is equal to m of s, that is equal to g of s by 1 plus g of s into h of s. Now, what is the output response of the system in S domain? The input into the transfer function. Therefore, we know already the transfer function from this. If you know the g of s value and h of s value, we can find m of s. Then multiply this with r of s. After that, you take the inverse Laplace transform of it to get the c of t. So finally, c of t we will get by taking the inverse Laplace transform of this product. So like this way, we can find the time response of a given first order system. Now, how to analyze the time response? The time response of the system basically consists of two states. One is transient state, second is steady state. That this is transient state and this is steady state. By the figure only, we can say that in the transient state, the response is not constant. It is varying from 0 to some value. That means where the response is changing from one state to another, then that state is called transient state. If you see in the steady state, the response is almost reaching the final value and stay at that final value. That means it almost constant. Therefore, we can say the steady state, the response in the steady state is constant, so that response is called steady state response, where the response is constant or stay within certain limits and it's very close to the final value, that is steady state. So in general, any system is having two states, either first order or second order. It is having transient state and steady state. So the response of the system c of t can be written as the sum of these two, sum of the transient response and steady state response. So in the transient response, it is a function of time, therefore it is changing from one value to another value as the time is increasing, and steady state value is almost a constant. At t is equal to infinity, it reaches the final value. So it indicates the final value of the system at t is equal to infinity. Let us take an example here of time response of a system. Here in this example, c of t is given by 10 plus 5t power minus t. Now, can you guess which is a transient response and which is steady state response? In the previous slide, we have seen clearly c of t is the sum of the transient response and the steady state response. Therefore, c of t, in this c of t function, e power minus t is the function of time. So as t varies, this term will change the value. So 5 into e power minus t is here the transient response, whereas 10 is a constant. So we know that at steady state the value of c of t is constant. That means at t is equal to infinity, the final value is a constant. So when you substitute t is equal to infinity in this formula, we have we have c of infinity is equal to 10 into 10 plus e power minus infinity, that becomes 0 term. So c of infinity is equal to 10. That means the steady state response is a constant, that is 10. So 10 is the steady state response. Like this way, we can find the steady state response and transient response from the given response. The motive of this, the idea behind this C of t, finding C of t in terms of transient and steady state responses is we can find the transient behavior of the system when the time changes. After that, it will reach a stable value or a final value and remains the same value for a long time, is called the steady state. So any system, when you give the input at that instant moment, it won't change suddenly its value, it won't respond. It will take some time to reach its final value, there it will stay constant. So any system in general will take some time to settle down. That's why when you analyze a system in time domain, we need the time response analysis and steady state analysis. So we can find or we can discuss this transient behavior as well as steady state behavior of a system. Now we will see what are the different test signals to test the given system. Why to apply the test signals here? The test signals are useful to find the system behavior for various kind of input signals. So let us see what are the different type of input signals to know the system behavior. Here we have four fundamental test signals. Those are impulse signal. Impulse signal is also called sudden shock because the impulse signal occurs only at an instant of time. Suppose that t is equal to 0, the moment comes, for rest of the moments t is not equal to 0 time, there is no impulse signal. That is called impulse signal. Suddenly some disturbance occurs to the system, so we can find at this point how the system behaves. And second one is step signal. The step signal is also called sudden change. So at this moment, we will give suddenly a signal and will maintain that amplitude continuously for the rest of the time. That is suddenly a change comes and that remains same. Again, it doesn't change. So that disturbance is a constant from the moment of occurrence. That is step signal. So from this step signal, you can find the system behavior if constant disturbance occurs in the system. Then ramp signal. Ramp signal is called constant velocity signal. So if the change or disturbance is occur at some time and keep on changing constantly, then we can find the system behavior in this case. That is nothing but ramp signal. Then parabolic signal, that is also called constant acceleration. When you give the constant acceleration, keep on changing the velocity and maintaining the constant velocity acceleration, then how the system behaves. So parabolic signal is used at that time. These are the test signals, standard test signals to know the system behavior. I think all these standard test signals covers in all kinds of disturbances practically in general occurred in the system. Now let us see the mathematical expression of the test signals, because we have to find the time response. Already we have discussed that the time response can be found by using the Laplace transform of the input signal and the transfer function of the system. So to get the Laplace transform of input signal, we need to know the mathematical expression of the input signal. So here we will see that mathematical expression of the test signals. First one is the unit step signal. The unit step signal is equal to 1 for t greater than or equal to 0, and it is equal to 0 for t less than 0. So this is the signal representation. It is also called sudden change. I told you already, suddenly the signal comes at 0 and remains the same for t greater than or equal to 0. This is called unit step signal. And the ramp signal is defined as, it is also called, I told you, it's a constant velocity. Means linearly it is changing from 0. Say suppose at 0 it occurs, then as t is increasing linearly, then the amplitude also increases like this. Therefore the mathematical expression is a into t, where a is the slope of the line. So it is defined as r of t is equal to AT for t greater than or equal to 0, else it is 0. That means when the sudden velocity occurs at t is equal to 0, so from t is equal to 0, it is AT. For remaining values less than t 0, it is 0. The next signal is the parabolic signal. It is also called constant acceleration. That means this is a parabolic curve shown here. The mathematical expression is a t square by 2. When you substitute t is equal to 0, it will be 0. When t is equal to 1, it is 1 by 2, that is 0.5 a at this point. When t is equal to 2, it is 2 square by 2, that is 4 by 2, that is 2 into a. So we have 2. Then for 3, it is 4.5 a. Similar way, we can take some values, so you will get the curve like this. This is parabolic signal. And fourth one is the impulse signal. I told you already, at t is equal to 0, you will get sudden shock, an amplitude signal, but the area under this pulse is equal to 1 or a constant. If it is unit impulse, it is equal to 1. Area under this curve is 1, otherwise it is a constant, take some a value. So this is impulse signal. Using this, all the test signals, now we will find the time response of a first order system. These are the time and Laplace domain expressions of the different test input signals. If the signal is step, the amplitude is A, that means the magnitude is not 1, it is a step signal, and its Laplace transform is A by S. If the signal is unit step, then it is 1, amplitude is 1, and Laplace transform is 1 by S. When the input signal is ramp signal, if it is magnitude is not unity, then it is expressed as AT. Therefore, Laplace transform is A by S square. When the ramp signal is unit ramp signal, that means the magnitude is 1. That is A is equal to 1. Therefore, expression is simple T. then Laplace transform is 1 by s square. When the signal is parabolic, its expression is a t square by 2. So the Laplace transform is a by s cube. When the parabolic signal is having unitary magnitude, then t square by 2 is the expression. Then its Laplace transform is 1 by s cube. For the impulse signal, the expression is del of t and its Laplace transform is 1. If it is a unit impulse, the magnitude is a into delta t. When the unit impulse is there, then amplitude is 1. These are the different test signals with their transfer functions. Now we'll see uh, the first order system time response. Before going to the time response of the first order system, let me explain how to find the order of a system. I will give a system or will have a system. How to say that the system is a first order system or second order system or any order of the system? So this is the way how to find the order of the system. We have a differential equation of a system. We have the differential equation of a given system. So this we have to write the differential equations from the given system. Already we have seen for mechanical and electrical system. After getting the differential equation, we can find the order from the differential equation like the maximum power of the derivative. What is the maximum power of the derivative? Is it 1 or 2 or 3? That indicates the order of the system. It is one way of finding the order of the system. Secondly, using Laplace transform. Using Laplace transform, how to find? We'll have the Laplace transform in Laplace transform in S domain. I mean, you can have the transfer function in S domain. So like this we can get. We have numerator term and denominator term in S terms. So the power of the S in denominator indicates the order of the system. So the maximum power here of S in denominator gives the order of the system. Here through the differential equations, the highest power of the derivative is in here, that gives the order of the system. Anyhow, we are solving the problems through Laplace transforms. So from Laplace transform, it's easy to find. It's easy to find the order of the system. Now let us move on to the time response of first order system. Take this through one example. We'll see how to find the time response of a given system, of first order system. Take this example. A given system is single loop system, and here the open loop gain or the forward gain is 1 by Ts, but the feedback gain is 1. Nothing is given means it is 1. Therefore, the transfer function C of s by R of s is equal to 1 by 1 plus Ts. Now, we will find what is the order of this system and we'll cross verify whether it is a first order system or not. By the previous explanation, we'll say the denominator term S power is indicating the order of the system. Here, the denominator is in the transfer function, we have 1 plus ts. So yes, power is 1. So it is first order. The order of the system is 1. That is how to find the order of the given system. Now we'll see the response of the system for the unit step. Any input you can take from the standard input signals. Here I will explain how to get the response of the first order system for the unit step input only. Now remaining test signals you can apply and you can test similar way. So this is the system given closed loop control system with open loop gain of 1 by st and feedback gain of 1 or unity feedback. From this we already know C of S by R of S transfer function is equal to 1 by st plus 1. Now how to find the response C of t? First we have to find C of S. So C of S is equal to the transfer function 1 by st plus 1 into R of S, where R of S is equal to 1 by S because input is unit step function. Now C of S is equal to 1 by st plus 1 into S. So since R of S is equal to 1 by S, it comes under denominator term, one more S term. So how to find C of t from this C of S? Since we have two terms in the denominator, we can follow the partial fraction method. But if you take the partial fractions, we can write this 1 by s into st plus 1 like a by s plus b by st plus 1, two terms, split it into two terms. That is the partial fraction method. Now take the LCM at the right hand side. We will get a into st plus 1 plus b into s by s into st plus 1. Now you compare the numerator terms because denominator terms are equal, numerator terms must be equal. So 1 is equal to a into st plus 1 plus bs. Now both sides equate s terms and constant terms. There you will get a is equal to 1 and b is equal to minus t. Therefore, from the first equation, C of S is equal to 1 by S because A is equal to 1 minus B is equal to minus T, so minus T by ST plus 1. That is equal to 1 by S minus T by, in the denominator if you take common T into S plus 1 by T. Therefore, C of S is equal to 1 by S minus T cancel, therefore 1 by S plus 1 by T. Now you can take the inverse Laplace transform for this so that you will get C of t. Therefore, C of t is equal to inverse Laplace transform of 1 by s is equal to 1. That is a unit step function. So u of t we have taken common, so keep it separate. So it is 1 minus 1 by s plus 1 by t. Inverse Laplace transform is e power minus t by capital T. So u of t is common anyhow. So 1 minus e power minus t by capital T into u of t. This is the time response of the given first order system. Like this way, we can find the time response of a first order system for any kind of input signal. One thing is you should know what is the Laplace transform of the given input signal and what is the transfer function of a given first order system. Then you can find easily through this method. Now you can express this mathematical expression of C of t in a graphical way like this. So we have the expression C of t is equal to 1 minus e power minus t by capital T into u of t. Take different t values. When t is equal to 0, it is simply 0 because 1 minus e power 0 is 1, so 1 minus 1 becomes 0. So we have kept, this is the point. At t is equal to 0, we got the magnitude, this C of t value 0. when t is equal to capital T. When t is equal to capital T, if you substitute, t by t will become 1. So e power minus 1 is equal to 0, 0.3, 0.36 something you will get. Then 1 minus 0.36, it will become 0.632. So keep a point here. Similar way, at t is equal to 2t, you will get 0.86, then 0.9 for 3t, like this. Then at t is equal to 40, we will get the point at this point, in similar way, and so on. You can keep it. At t is equal to infinity, we substitute t is equal to infinity here. E power minus infinity will become 0. Then 1 minus 0 will be 1. So 1. It will become 1 at t is equal to infinity. So this is exponential rising function, this expression. So graphical way, we can show the response of the system like this. Now let us move an example. Here I have given one example for your practice. So the given first order system is here. The block diagram representation is not given for the system. Directly the transfer function t of s is given. So t of s is equal to c of s by r of s, that is equal to 2 by s into s plus 1 into s plus 2. So in the denominator we have three terms. So similar way you do this practice it using partial fraction methods. Here you will get three terms a, b, c, then solve for a, b, c and take inverse Laplace transform, so that you will get the response c of t for the given response, given input. Here the input is given as a unit impulse function. So unit impulse function, Laplace transform is 1 here, so hint is also given. Therefore, solution, you will get c of t is equal to 1 minus 2 into e power minus t plus e power minus 2t. So solution is also provided. So it is for cross verification after practicing this problem. So please, I hope you practice this problem so that you can understand how much you understood actually this topic. Now let me come to the summary point. What we have discussed in this video. In this video we have learned what is meant by time response and why to find the time response of a given system. Then we learned what is the order of the system, how to find the order of the system. Then we learned what is meant by transient state and what is meant by steady state, and how to identify these two states in the given response. And also we have learned the time response of first order system for the given input signal. In the next video, we will learn about the second order system and the time response of the second order system with its time domain specifications. Thank you.